Welcome to another video on digital electronics. In this video, we'll be studying excitation table for all the flip-flops. Before doing that, let us understand what is excitation. For example, I have an SR flip-flop here which has output Q and Q bar, its complement. For example, the current state, that is the present state of this flip-flop, is Q is equal to 1 and Q bar is equal to 0. Say the next state after one clock pulse, I want this to become 0 and I want this to become 1. Then what is the input at S and what is the input at R that I should be giving to get this specific output? It could be also possible that the current state of the flip-flop is 1 and 0, and in the next state I want to keep this as 1 and this as 0. I do not want to change. Then what is the input at S and what is the input at R that I should be giving? How should I excite this flip-flop in order to get the required output? That is the meaning of excitation. So let's see how do we find the excitation table. For that we have to start from our basic truth table, then move on to the characteristic table, and then finally get the excitation table. So it is very simple. Truth table is as shown here, which we have been doing since the start. For S equal to 0, R is equal to 0, you will get Qn, there is no change. For 0, 1 you will have 0, for 1, 0 you will have 1, and for 1, 1 you will have an invalid state. That's your basic truth table. Coming to the characteristic table, in the characteristic table now, we will first have S, R and present state. For given SR and the present state, we will find out what is the next state of that flip-flop, right? So we'll have 3 inputs in this flip-flop, right? So SR, since SR and QN, since there are 3 inputs, how many combinations will I have? I will have 8 different combinations from 0, 0, 0 to 1, 1, 1. And depending on these combinations, I will use my truth table to get the value of Qn plus 1. Let us see how do we do this. So you first have to write down all those 8 values and then we will find out the value of Qn plus 1. I have pre-written it so that I do not waste much of time in the video. We will just verify all the values. So S equal to 0 and R is equal to 0. For S equal to 0 and R is equal to 0, what is my Qn plus 1? It is nothing but Qn. So my Qn plus 1 will be Qn. But what is your Qn at this point? It is 0. So your value will be 0. Again for S equal to 0, R is equal to 0. What does your truth table say? It is Qn. But what is the value of Qn? It is 1, so it will be 1. For S equal to 0 and R equal to 1, in both these states, for 0, 1, what is the value of Qn plus 1? 0. So you straight away write here 0 in both these conditions. For 0, 1, for 0, 1. For 1, 0, my output is 1. For 1, 0, I do not have to even see this. For 1, 0, straight away it is 1. For 1, 0, straight away it is 1. And for 1, 1, it is invalid state. So for 1, 1, we will write as invalid state, right? Which does not exist. So this is how I have written the characteristic table. What does the characteristic table mean? It means for given S and R and the present state, what is my next state? If you see properly, this 8 combinations that we have covered all the 4 combinations of SR, 0, 0, 0, 1, 1, 0 and 1, 1 with both the values of the present state. Present state could be 0, could be 1, could be 0, could be 1, could be 0, could be 1 and could be 0, could be 1. There is no other combination possible for this SR flip-flop. Now using this characteristic table, we will find out the excitation table. What did I tell excitation is? Excitation means given a flip-flop, what is the value of S and R that I will have to get a particular value of Q and Q bar, right? So for excitation table, we will write down Qn and Qn plus 1. Present state is 0. I want 0 as a next state. Present state is 0. I want next state as 1. Present state is 1, I want next state as 0. Present state is 1, I want next state as 1. So how will you find this from the characteristic table? For 0, 0, you have to see Qn and Qn plus 1. Qn and Qn plus 1. 0, 0. For 0, 0, what is your SNR? 0, 0. Again you have a 0, 0 here, and here you have 0, 1. Which means S is fixed to 0, but R is 0 or 1, means I can write S0 and R as don't care. I hope this is clear. Similarly, you can solve for all other. For 0, 1, Qn and Qn plus 1 is 0, 1. So Qn should be 0 and this is 1. So I find here one single combination like this. For this, my SR is 1, 0. So I will straight away write it 1, 0. There is no other combination with same value of 0, 1 here, right? You only have 1. For 1, 0, you have 0, 1. So I will write it 0, 1. And finally for 1, 1, see I have 1, 1 here and I have 1, 1 here. For this, S is 0, S is 1, which means I will have a don't care here. And this is 0, 0. So you will have X and a 0 here. So this is how you end up writing the excitation table for SR flip-flop. The best way to remember this is you remember 2 cross at the extreme ends diagonal, and then you write 0, 1, 0, 0, 1, 0. Because while solving numerical problems for counters and other things, you will have to remember this excitation table. So the best way to remember this is 0, X, X, then 0, 1, 0 and 0, 1, 0. Let's move on to the second JK flip-flop. So we will again, the procedure remains same, there is no change at all. So you start with the truth table. So this is the JK's truth table. I hope you remember by now. It is same as SR except for the last state which was not defined there, and here we have Qn bar. From this we find out the characteristic table. Characteristic table will have J, K and the present state. We will find out what the next state is. Since you have 3 combinations here, 3 inputs to take care of, I will have 8 different combinations over here. From this 8 different combinations, we will write the value of Qn plus 1. So we will solve 1. I will draw a line here for simplicity. For J equal to 0, K equal to 0, what is your output? Qn plus 1 is nothing but Qn. So my Qn plus 1 will be same as Qn. For 0, 0, I will have 0 here and 1 here. There will be no change. For 0, 1, it is 0. So for 0, 1, both are 0. For 1, 0, both are 1. Now look at the last one. For 1, 1, it is Qn bar. So for 1, 1, my output Qn plus 1 will be Qn bar, which means Qn, if it is 0, I will have a 1 here. If it is 1, I will have a 0 here. And using this characteristic table, now we will solve the excitation table. So excitation means what? What at the output, if I want the specific output, 4 different, since there are only one Q that we are calculating for 2 different states, right? So we can have 4 combinations. So currently Q is 0, I wanted 0, it is 0, I want 1, it is 1, I want 0, it is 1, I want 1. So 4 different combinations of the state, that is called the state of the flip-flop. To get that particular state, what is the excitation of J and K that I should give? So I would find here Qn and Qn plus 1 as 0, 0 and 0, 0 here. So see, for this Jk is 0, 0 and it is 0, 1 here, which means J is 0 and K is X. So J is 0, K is X. Similarly, you can solve for the other ones. For 0, 1, Qn and Qn plus 1 is 0, 1. So here I find it 0, 1. Here also I find 0, 1. This is 1, 0. This is 1, 1, which means it is 1x. So it is 1x. For 1, 0, this is my 1, 0 and my 1, 0. So for 1, 0 and 1, 0, it is 0, 1 and 1 1, which means it is x and 1. So I have x and 1. Similarly, the last one for 1 1, for 1 1 here and here I have 0 0 and 1 0, which means I have x 0. So this is x and this is 0. So how do you remember this? Diagonally remember x. Now there are two x's diagonally, and you have 0 1 1 0. This is the best possible way to remember the excitation table. Let's now move on to the last two flip-flops. These are small flip-flops. So we have truth table. For T flip-flop, characteristic table here, since I have T as a single input, so I'll have T and I will have the present state, and for this I will find out what the next state is. So how do we do this? T is 0, 2, right? So I have 4 combinations. T is 0 and present state is 0. What should be my next state? For T0, my next state is Qn. So it will be same as Qn. T is 0, output will be same. For T1, my output is Qn bar. So see here, T is 1, your output will be Qn bar. So Qn is 0, my output is 1. For T1, my output is 0 because my Qn is 1. It is complement. Now from this we have to find out the excitation table. So for 0 0, my excitation is 0. So for 0 0, excitation is 0. For 0 1, my excitation is 1. It is 1. For 1 0, 1 0, excitation is 1. And for 1 1, my excitation is 0. So this is how we write the excitation table from the characteristic table. Same way, exactly same way, no change. You can go ahead and solve for yourself for D flip-flop. Pause the video, check for yourself whether you're getting the same excitation table or not. So this is the truth table. For 0, you have 0. For 1, you have 1. Characteristic table, current input and the current state. So you have 4 combinations, 0 0 0 1 1 0 and 1 1. For D0, what does the truth table say? D0, my Qn plus 1 is 0, right? So D0, this is 0. Whatever is the D will same get repeated here. There is no thinking, absolutely no thinking here. So 0 will become 0, 1 will remain 1, right? Now from this we have to find out the excitation table. So excitation table is Qn and Qn plus 1, current state and next state. What should be my D? So for 0 0, it has to be 0. For 0 1, it has to be 1. For 1 0, it is 0. And for 1 1, it is 1, right? So this is how you write down the excitation table. So we have completed all the 4 flip-flops. I hope you understood how to find out the excitation table. I'll stop the video here. Thank you for watching.